Okay, well, thanks, Fred, and it's a pleasure to be on the other side. And I normally listening to your webinar, so thanks for having me on this week. And welcome everybody to the webinar today. And I realize, I guess probably many of you are maybe more focused on reliability matters, given that you're part of the Ascendo group. But I think that one of the key connections here is that statistical process control is, I would say, sort of a prerequisite for ensuring ongoing high reliability. So we're going to talk a little bit about SPC, and I've done this webinar a couple other times. There's a good amount of material. I did cut a little bit out. So, I mean, if you have questions that come up during it and if something's not clear and you would like me to clarify, feel free to post something on the chat window. But other than that, I'll plan to take questions at the end. But I don't mind being interrupted if there's something you feel like it's more relevant to bring up at the time. So by way of agenda, since some of you may or may not be familiar with what SPC is all about, before I talk about 10 important aspects of SPC, I thought I'd just spend a couple minutes, maybe 5 slides, just giving you my take on what is SPC, what's the purpose, and some of the background. And then we're going to kind of charge through, I think, 10 important items. There's probably more than 10, but this is what I thought of when I sat down to do this talk to help summarize some of the key aspects of SPC. But we'll spend time, not the same amount of time in each one, but I'm going to just highlight a few of the important aspects of SPC. I won't read them to you now since we'll be going through them individually. So first of all, what is SPC? Really, it's nothing other than a way to monitor a process, a system, with the goal of being proactive to prevent problems from occurring. One of the challenges with SPC implementing it is understanding what the benefits are, quantifying them, because problems that have been prevented are sort of hard to quantify because we don't know what would have gone wrong. Yet we know from a lot of bad things that have happened that have cost lots of money, we've gone back and seen that, gee, had we only been controlling this key input parameter that changed, we would have avoided a multi-$100-million problem, perhaps. I could point to several, including Firestone Tire, Fiasco, and others that could have been prevented with proper use of SPC. So you can think of SPC as sort of using the voice of the process, since the process generally can't speak to us, although maybe with Alexa now that'll be changing. But really, the data that we can collect from our process becomes the voice of the process. And control charting, or SPC, is the way in which we make best use of that data to help make decisions with regard to whether things are behaving in a normal or typical pattern or something that's behaving different than before. The nice thing about SPC is that it gives us objective criteria for knowing when to act and when not to act. Left to our own devices, it's kind of like trying to time the stock market. We usually make the wrong choice. We sell too soon when on a dip, or we buy after a huge run. And a lot of times, same thing can happen when trying to look at processes. It might be overreacting to what we think is a signal, but it's not really so unusual from a probability standpoint. So it's going to help us distinguish, when do we need to react? What is a signal versus the everyday variation or noise that occurs? But essentially, the big thing is this is a tool to help us prevent issues from occurring that generally are pretty costly. The other key, I think, principle of SPC is that, we want to do a lot of other things with our products. Like, we want them to be reliable, we want them to be capable of meeting spec, and so, but only when we have a process that's predictable, that's behaving in a predictable fashion, can we actually, number one, produce a predictable output, but also, number two, can we actually characterize the capability or the reliability of the product. I know a lot of you get involved with reliability prediction, but if we're dealing with a process that's highly variable and changing a lot, any estimates that we developed based on a sample of a changing process are probably not going to be very predictive of what we'd expect to see. So it would almost invalidate all of the good work that's done to ensure highly reliable products if we can't even achieve stability in important process inputs. Another principle, and this is something that Deming was trying to teach us, was that really this idea that we can inspect quality into the process just by checking everything that we produce is really a fool's game, and that really, if we want to be proactive and efficient, we should be using proper sampling methods and ensuring stability. And then actually, when you're doing a good job of that, you can actually kind of get rid of a lot of the costly and imperfect inspection systems that exist. Just a quick bit of history, and part of the reason I'm going to bring this up is a little later on I'm going to talk about some of the issues with some of the charts, the original charts that were developed. A lot of them still work fine, but there are a lot of situations. I just wanted you to appreciate, like this tool, this control charts were developed back in the 1920s by a guy named Walter Schuhart, and then another big pioneer in championing these methods was, of course, W. Edwards Deming, who had a huge impact, especially in Japan, helping Japanese manufacturers who were decimated really after World War II kind of rebuild industry and actually leapfrog many of the other manufacturers around the world, including our own automotive industry, unfortunately. I would say today, I still feel like the deployment and the success of SPC is somewhat mixed. I go into some companies and it's clear they really understand, how to deploy SPC. They're controlling the important characteristics. They're using the right kinds of charts. They're using appropriate sample sizes to detect important changes. They kind of have spent the time up front to really make the best use of the tool. Other places, it's sort of like, well, we got to have these charts because our auditor's going to come in and make sure they're on the wall. And they kind of don't even really understand what the purpose of SPC is all about. So I'm still not, despite the tool being rather straightforward, it's not very, compared to say doing a accelerated life test or analyzing reliability data, it's quite simple, yet I still feel like it's misused or underappreciated in many places. So Deming, he said a lot of things, right? A lot of books you could read, but part of this ties into one of the issues we'll talk about later in terms of operator responsibility. But essentially, management's responsible for quality, especially when it comes to ensuring that the typical or common cause variation is acceptable. We rely certainly on operators and tools like SPC to detect changes from that level of variation, but really we shouldn't implement SPC and say, well, the operators are going to make sure we have perfect products now. It's totally up to them. A lot of the causes are going to be out of their control. I mentioned the idea about inspection, and just in general, SPC is one tool, but I think again to make really adequate use of this method, we're gonna have to rely on some other methods, perhaps design of experiments to really understand what are the critical inputs to the process that are worth controlling, and by how much do we need to control them, right? Because it's one thing to say we're going to keep things stable, but how stable is stable? And so one issue is how much can, say, an operating pressure vary before it's going to actually cause a problem with product performance. We need to know these things in order to develop adequate control systems. So hopefully this idea of a system that helps us diagnose a process and assess this characteristic of stability makes some sense. That's what statistical process control is. Now there are some other tools that sometimes get linked into an SPC program, but I'm really focusing on the control chart in this stuff. All right, so then we're gonna go ahead and move into what I'll call the 10 keys. The first one being, let's before we do anything, let's make sure that we have a good understanding of what the purpose is. I kind of alluded to this in the introduction, right? So control charts are going to tell us when a system or process has changed. And we have a word for that. We call it out of control or unstable. Now, unfortunately, some of these people who are not meeting spec, or they might say, oh, the process is out of control, because just naturally that seems like English we should be using. That's not technically correct. We could have products that routinely are going out of spec, but they're perfectly in control. Okay, we'll see that more with some pictures coming up. But again, the purpose of SPC is to tell us when there's been a change in the process. Even if we're meeting the requirements 100% of the time, we still might observe a change, and we ought to at least be interested in knowing that a change has occurred, okay? Especially if we've validated our process at a different, say, mean value or different degree of variation. Now, this idea of ensuring that we're in spec or not, of course, is very important. That's not the purpose of a control chart. The tool or method that we typically use to assess the ability of a process to meet specification is referred to as process capability analysis. And I'd say the one link is that before we would do such an analysis, we ought to first have evidence of a stable process. So the control chart would come first, assuming we have a stable process. Then any estimates that we would make of its capability are sort of predictive in nature because they're coming from a process that's behaving predictably, that's stable, right? If I go to a restaurant and one day, the food is delicious, and the next day, like I get sick, and the next day it's sort of mediocre, I can't look at it, but you never know like what you're going to get on any given day, right? But then another restaurant who's consistently very good, you could order different things, but you know that this restaurant is, like, from a capability perspective, behaving in a very good and stable fashion. So anyway, hopefully that distinction makes some sense to everybody. Now, I want to just sort of conceptually show you what it means to be in control or stable. The tool we use, of course, is the control chart, but that's really a diagnostic tool, an efficient diagnostic tool. But really, in the back of your mind, when you're staring at a control chart that looks stable or one that looks unstable, what kind of picture should we have in the back of our mind? I just want to spend a minute on here. Suppose I collect some data on a critical dimension. Here's a radius, say, of a spring, and I draw a distribution. I've kind of turned the distribution 90 degrees from the way we normally look at it, where the mode is sort of in the vertical direction. I did this kind of because if we were going to chart this data, it would be, we'd have like an upper control limit, a lower control limit, and we'd actually be plotting statistics that represent this data. But nevertheless, this curve or distribution represents how the sample data stacks up. If you like, you could think of it as a smoothed out histogram. Now, let's suppose this particular distribution was developed at a point in time, over a fairly short period of time, and it represents my process, let's just say, over a 1 hour window, high volume manufacturing here. Now, if I were to repeat this sampling effort, every hour I collect a bunch of data, and I draw the distribution that's represented by that data just simply by stacking up these points or drawing developing histograms. And if I notice that over time, going back into the slide here, that the distribution is roughly the same, and we could characterize the distribution by some key statistics such as like the mean or the median. Maybe the median is more appropriate in this case since it's clearly not symmetrical and not normal. And we could also characterize the variation by perhaps standard deviation. But even just visually, if I look at this picture, I see that over time, the distribution is not changing. Now, at a given time or over time, of course, I'm going to get different numbers because I might get data points from different parts of the curve. But the overall distribution, like the range and the typical values I see, are not changing. I see the note about getting further from the mic. I'm wearing a headset, so I'm not getting further away, but I'm not sure if there's another technical problem that we're having with the mic. So keep me posted on this issue. Now, contrast to the previous slide, what if we're dealing with a process that is clearly not stable? That would mean that essentially the distribution is changing over time. So at time, first hour, second hour, things look the same. And later points in time, I'm seeing either a process change, a process drift, or perhaps the amount of variation is changing. And so this is a picture of something that we will call unstable or out of control. Now notice, I haven't said we're in spec or out of spec. It could be that the spec limits are very far away from the data, meaning, it could be that the lower spec is all the way out here and the upper spec's out here. I'm not saying that necessarily that we're out of spec. Whether we're in or out of control has really nothing to do with whether we're in or out of spec. So just kind of keep that in mind. I'm talking about, does the mean value, is it behaving, is the process producing a typical value, central tendency that's similar to what we had before? Or is the amount of variation we're seeing similar to what we had before? Now, since we're not going to be drawing these distributions over time, and we could do this, there's going to be a much more efficient way to do this. What we're going to do is we're going to take samples from the process, and we will calculate some statistics which describe or represent that process at a point in time. You can see here, I'm taking, all these dots represent 100% of the data that parts I'm producing. If I were to take, say, 5 consecutive parts and measure them and calculate their average and their standard deviation, and begin placing those on the relevant control charts, and then wait a period of time, take another subgroup, another sample, calculate the relevant statistics, and then continue on. At some point in time, I'll have enough data on my charts to establish what we call control limits, which we're going to talk a little bit more about in a second. But essentially what I'm doing is I'm sampling from the process, and I'm capturing essentially what that process is doing at a point in time. I completely agree with your comment, Dennis, about specs are sometimes arbitrary. And so that further makes the point that we need to be concerned about stability, because, if we're running, let's just say we're typically running near the nominal value and everything's wonderful, we never have a customer problem, and all of a sudden the process shifts, we're not out of spec yet, but we're running near one end, it would be sort of incorrect unless we've done some serious validation and testing across the specification range. It'd be wrong to just assume that the specs are perfect and that anything in spec is going to result in, wonderful product performance. So that's why when we see a change that we ought to react, even if we're not out of spec yet, because maybe the specs weren't appropriate. And beyond that, variation, any unnecessary variation, like variation due to process changes, that's something that clearly we could understand what's going on, and no variation that's preventable should we accept. Customers would prefer less variation in general. All right, so I kind of illustrated the sampling process. We could continue and develop, say, an X bar chart, which monitors the average or location of the process. We could develop an S chart. Sometimes range charts are still used to help monitor variation. I prefer the S chart. This is going to monitor kind of like the short-term variation. And we're not going to get into the mechanics of chart construction here, but the idea here is that this control chart is essentially monitoring the state of the process. And the idea being that if this process continues as is, with no changes, even if it's out of spec, we would expect the process to appear stable on a control chart. If the location's not changing, we would expect the X bar chart individuals chart to look stable. If the degree of variation is not changing over time, meaning the width of these curves is not changing, we'd expect our variation chart, like the S chart, to remain stable as well. All right, so hopefully this clearly, people are clear on what the purpose of the control chart is. It's to monitor the current state of the process. The other thing I would say is that the other thing that this charting mechanism is supposed to do is to help us distinguish between common cause variation, which is nothing other than the variation we see like this described by our particular distribution data, versus special cause, which is the variation we see when the process shifts or the curve gets wider or narrower. And if we set up a chart correctly, the control limits should reflect or account for common cause variation, but should not reflect special cause sources of variation. Because after all, if they do, then we're going to make our chart insensitive to detecting special cause sources. So special causes are things that are not part of the everyday process that could creep into our system, perhaps a material change or even a lot-to-lot change, or maybe design change that was made that we didn't know about could cause a change in our process. And that's something that we're trying to detect on the control charts. So just to kind of finish that thought off, when we have a stable process, really the only variation that's present is, of course, common, because that's always there. When we have an unstable process, that implies that we have one or more special causes going on. The whole purpose of the control chart is to detect these special causes, not just so we say, well, that's nice, we have a special cause, and go make an adjustment, but the purpose is to actually attempt to determine what is the root cause and systematically attempt to eliminate the subsequent opportunities or chances for these special cause sources of variation. All right, so that one was a kind of a longer key. The next one I want to talk a little bit about is the extreme criticality of focusing on the important parameters or characteristics to chart. We obviously cannot control every possible process output and process input. I will say that we want to try to move upstream, backwards, meaning you can like just start plotting proportion defective, right? The problem is once you go out of control, it's not really clear what caused it. To make best use of SPC, we really need to do some upfront work to try to determine what are the key input characteristics. And a lot of times they're back up in the supply base. What should your supplier be controlling? What should we be controlling? Like material properties, dimensions of incoming purchase components, processing parameters like temperatures and forces and speeds that we can control that might change. What is it that we have control over that will, if not controlled within a certain range, will impair product performance? They may affect the quality, the fit, may affect reliability. These are important questions because if you're just going out there and guessing on a few characteristics to chart, you may have wonderful looking control charts, but you're really not changing, you're not really preventing the real problems. So I would say some upfront work needs to be done unless you already know. In some cases, your customer will tell you exactly what they want you to control that they feel are critical if you're supplying components to another tier, say. Sometimes you'll be told what to control. In that case, that's the minimum you have to do. I would still look for other input factors that your customer doesn't even know that you should be controlling, that you can figure out that you should be controlling. But only when we are controlling those key inputs will we really achieve predictable, capable outputs. It's like a tennis serve. I've been struggling with this for a while, and I'm trying to take a viewpoint like, if I can understand the 4 or 5 really key things so that I can get, I don't know, like 75% first serves in with the right accuracy and the right speed that I want, then I'm golden, right? So it's things like, where's my toss need to be? Where's my grip need to be? how far does my racket need to drop behind my back to get the right whip on my stroke. So focusing on those key inputs and making sure we reduce variation of those inputs will sort of allow the process to take care of itself. Now, how are we going to focus on these key characteristics? Well, the tools, start with very sort of brainstormy type things like cause and effect fishbone diagrams to much more quantitative tools that I do a lot of work in, like design of experiments. But essentially, you're going to have to pick some tools that you're comfortable with to help identify what are the likely inputs. This is more of like a cause and effect diagram, but it's the same idea where we'd identify what are the key inputs that are going to produce some effect. Dennis, I see your comment about DOE being underutilized. I agree. It's hard for me to see that because in our consulting business, we probably 80% of it's DOE work. So we're doing tons of DOEs every week or every month. But I agree that when we walk into a presentation with, say, I don't know, a VP of manufacturing or product development, and we show them the results of a DOE, they're sort of, or what can be done. It's almost amazing to me that it's even surprising to them that this tool is so readily available and accessible and so powerful to help not just solve problems, but identify cause and effect relationships and identify key characteristics so that we can better use tools like SPC. So yeah, I agree, it's underutilized. I don't think I need to spend a lot of time on a fishbone diagram. This is just an example of a more qualitative tool to help identify key inputs. And this is more of a cause and effect. We have a problem of poor gas management. What might be the causes? But similar to be what would be the key, say, material or manufacturing inputs that would lead to a reliability or quality issue or not meeting some performance requirements. And then, of course, design of experiments. We have a soft spot for DOE in our company, and we just find that this to be an invaluable tool to, in a very efficient way, consider many sources of variation of inputs, and not just the individually, but very often variables will interact with each other, and it's some combination that results in a problem. And so without DOE, it's sometimes very hard to understand how factor interactions can lead to an issue in some important process outputs. With proper DOE, we can sort of see those immediately and help us determine, how to make our system more robust, or what do we need to control to perhaps make other sources of variation not so important anymore. All right, number 3. How about measurement systems? I mean, honestly, this is not my favorite topic in the world. When I get a phone call saying, will you help me with gauge R&R, or will you come teach a MSA class, I never get that excited, although it is critical to do it. It's just, to me, not the most exciting thing. It's not one of the necessary evils. But clearly, SPC, like DOE, is a data-driven tool. If we do not have an adequate measurement system, we are not going to have success in interpreting the data that we get. And specifically with a control chart, if we have a lot of measurement error, and that measurement error manifests itself in when we're collecting the data for the control chart, that additional error is probably going to show up and sort of drive our control limits wider than they ought to be. It's going to make it difficult to actually see the process changes that we're trying to detect. Or we might, have control limits that do reflect process variation, but we might be getting measurement errors that creep in that lead to out of control points. So here we're chasing around trying to figure out why the process is out of control when it's nothing other than a measurement problem. So in fact, SPC is actually a very good tool to monitor a measurement system over time. Sorry for a lot of the words here. I'm just kind of trying to paraphrase through these. Always a trade-off between what can you take away and refresh versus just a graphic. But I will say this, that very often people focus on gauge R&R, and that's an important piece, but it's one piece of a measurement system characteristic that's important. It specifically addresses precision or the lack of precision, which we usually break down into the repeatability, reproducibility components of precision. But there are other important issues. The measurement system has to be able to discriminate among parts that we produce. We have to make sure that we're accurate. If there are linearity issues, meaning that the ability of our measurement system to measure accurately or precisely may vary across the range of parts that we use this measurement system for, right? We need to know that, right? If the measurement system is very effective for 1-inch parts, but not very precise or accurate for 2-inch parts, it's a linearity issue. Finally, stability. What we've been talking about in this webinar, there's no guarantee because we did a gauge R&R and accuracy study today that 2 months from now that the measurement system is still performing the same. We might have new operators, we might have a new gauge, the gauge may have been dropped. Obviously I think people are familiar with the need to calibrate and that kind of stuff, but we ought to be ensuring that things like precision and variation in the measurement system are stable. So techniques exist for all of these important aspects of the measurement system. And in short, going through a validation of measurement systems is always the first step before we implement SPC, before we do a designed experiment, before we do any kind of data analysis. We want to make sure we're actually making judgments about the process and not just doing a bunch of measurement. All right, so this is just a typical 6-graph panel from Minitab, what you get when you do a gauge R&R. And honestly, none of these pictures tell me what I want to see. The first picture I do, I have to make by hand, which is, hey, show me every measurement by operator, by part, so I can actually see the raw data. And a lot of times things jump out on that you can't see here because everything here is average. So anyway, I'm going to sit there and beat up Minitab on gauge R&R output. All right. Let's move on. I know I'm sort of just flying through these. So hopefully, we all agree that measurement systems is an important one, even if you don't like doing HRR. How about number 4, choosing the right chart? This is kind of one of my pet peeves, I guess. There are a lot of things to get right, I think, in implementing SPC. And I'm not going to sit here and bash like XBAR charts or some of the older charts. They still work fine in many cases, but very often in some, especially more modern manufacturing settings, they're not appropriate, or they will send a very misleading picture. But other factors to consider, things like, obviously what kind of data. Am I dealing with continuous data or attribute data? Sometimes the data could be continuous, but we don't see much variation because our measurement system doesn't discriminate. So it's really behaving like attribute data. Okay. What sensitivity do we need to detect on a chart? What does that mean? The whole purpose of, as I said at the beginning, of control charts is to tell us when processes change. So the natural question that should be asked next is, okay, if the purpose of my chart is to detect change, how much of a change is something that I really want to know about? This is a practical question. It's not a statistical question. So you better have some idea, like how much of a change would maybe make your CPK not acceptable, or that would affect process performance, because that's needed, because we don't want to be going out of control for small process changes that are practically having no effect on our customer. And we certainly don't want to miss signals that are important. So for whatever reason, this whole concept, I don't see discussed or appreciated. There seems to be a lot of emphasis, and even consultants that say, there's no need to go do anything other than an individual's moving range chart. But the problem with individuals charts is they only will reliably detect large process changes. If you're okay with waiting like 7 samples until you see it change, go for it. But sometimes we want to very tightly control a process. Maybe it's we're trying to minimize the use of palladium or some expensive coating. We want to run close to the spec limit. We need to be able to detect small process changes. So we need to use charts that are good for that, like bar charts, use some charts. Another key thing is, does the process introduce variation from more than one source? Like, what do I mean by this? Like, think about injection molding or filling. We've got multiple filling heads. If you're sampling across different locations, like different cavities in injection molding, there's the opportunity that the cavities are not statistically the same. When you go off and do like X bar S or X bar R charts in the traditional way, you will run into some problems. And I have an example coming up. So there's a few others here that affect the kind of chart. I mean, are we doing a lot of short production runs? We don't want to keep setting up new charts. Do we have natural trending in our data that we need to accommodate in our chart? Those kinds of things. So there are charts that handle many of these situations, but I find that a lot of people just aren't really taking advantage of those techniques. So I'd elaborate on a few of these. I'll just kind of paraphrase and kind of move on here. But some of the traditional charts like IMR or XMR or XR charts, they were developed right at the very beginning, right, in the 1920s. And they still work great for many systems, but manufacturing then was very much serial. Produce a part, produce another part right behind it, another part right behind it. We didn't have a lot of multi-spindle, multiple cavity, multiple filling, and those present some unique challenges. And what we're seeing in most companies is that they really have needs for some of these newer techniques, the within and between charts. It's go by different names, but essentially it's a trio of chart where you're monitoring variation between subgroup, within subgroup, and then the variation, overall variation. We don't really have time to go into the great detail here, but I do have an example here where suppose you're charting, you're taking a sample in 3 locations on the same part, perhaps to save cost, and you're hoping that the within part variation is a proxy for between part variation, but that's not the case here. You can see here that the sample, like the top location on this time series plot is consistently running above the middle, the bottom is above the middle, which is above the top. If you were to take this data and just construct an X bar R, X bar S chart, where your sample is one from each location here, what's going to happen on your X bar chart? The averages are all sort of pretty close to the center line. They're all sort of like within 1 standard deviation of the center line. Now you might look at this and say, we have a really in control process. That's wonderful. I mean, that would be the wrong conclusion because we don't expect to see the averages all hugging the center line this way unless it started using the full range, and then we maybe evolved to this by reducing variation. What's going on here is that the control limits are entirely inappropriate because they're reflecting the within sample variation, which is including this location to location variation, which is significant. But this control chart is supposed to tell us sample to sample, monitor sample to sample, like tell us when the process changes. It's just we can't do that due to these location differences and the fact that the control limits are far too wide. So my goal here is not to make you an expert in these charting techniques. It's just to make you realize that there are a lot of situations come up where you need to maybe go away from the traditional chart. Here's that same data on the within between, the X bar, RB, and S chart trio, if you will. Things look a lot more reasonable. The next 2 slides, I'm not going to go through these. I just kind of highlighted for variable data. What are sort of there are a lot more charts that are on here, but these are what I view as the standard set that we should be picking from. I mean, honestly, I would not do X bar R, I would do X bar S, but they essentially have the same applications. Depending on the sensitivity needed or cost of sampling, you may use individuals charts. You have to understand their limitations. More often than not, if I'm dealing with individuals, I'm going to jump down to a QSUM chart or a DWMA chart, which allows us to really improve the ability to detect changes. And then so on and so forth. We've got the short run charts and charts that are good for handling multiple sources of variation like the one I just showed you. And then there's a group of charts for attribute data, and there's some others as well. that allow us to monitor things like proportion defective or number of defects. A lot of times we want to standardize these charts to make them a little more either visually pleasing or more applicable, generally speaking. All right, so again, if Fred mentioned this course, of course, that course will go through the gory details of all of these kinds of charts. Here, I wanted to at least make people appreciate the different kinds of charts that are going to be needed depending on the application. So if you're worried about the time, I guess the good news is the ones towards the back are rather short. So I think we're doing okay. I want to spend a minute talking about spec limits versus control limits because it's still shocking to me that this is still so confusing and people are sort of thinking that control limits are spec limits. I know no one on the webinar thinks that, but anyway, what are control limits? Limits, I like to think of them, there's a phrase I use. They're limits of expected variation in whatever statistic that we're charting. It could be the expected variation of averages on an X bar chart, expected variation among standard deviations on the S chart, expected variation on deviations from nominal on a short run chart, assuming that the process is stable. So if we start to go beyond these control limits, then that's something that we don't expect. We're seeing variation that's not common anymore. It's special. Now, what about spec limits? Spec limits have to do with limits of conformance for usually individual parts or individual values. Control limits are usually not pertain to individual measurements unless we're dealing with an individual chart. It's an expected limit of variation on some other statistic that we calculate perhaps from the raw data. Control limits should never just be set based on, oh, let's put them like 10% inside the spec limits. I've seen this go on. It just shows a complete lack of understanding of what control limits are supposed to be. For us to know what the limits of expected variation are, we have to collect some amount of data, maybe 25, 30 subgroups, and then calculate the limits based on what we've observed. And then assuming things are stable, then they become actually limits of expected variation. So these two kinds of limits differ on almost every aspect you could think of. Like who determines them, right? Spec limits are set by a designer, an engineer, a customer. Control limits are set by the process, right? The process gives us data. That's what determines control limits. Spec limits are supposed to reflect what's needed to make the product function. Not always, but that's what they're supposed to be. Control limits reflect how much process variation there is. Spec limits are used to assess capability or conformance. Control limits are used to assess stability. And then finally, spec limits, not 100% of the time, but usually apply to individuals. Control limits usually apply to general statistics. Okay? So don't mix these guys up. Now to test your sort of understanding of this, I always spend a minute on this in our classes. I like to ask this question. First of all, again, it's a little unfair because we haven't talked too much about setting up control limits, but let's just suppose on the X bar chart, it's very typical or traditional to draw these control limits at a distance of 3 standard deviations from the mean. So that sort of implies that, you'll get upset if you ever introduce anything about probability when you're talking about control limits. So I've got to be careful. You'll yell at me. I don't know what I'm talking about. But anyway, the plus or minus 3 sigma technically didn't have to do with the normal curve, but it's still a valid thing to draw on here. But you might know or realize that if I go out plus or minus 3 standard deviations, that's going to trap around 99.7% of whatever is under this curve. In this case, they're averages. So here's the question. I've got this control chart here. It appears to be stable. There's nothing beyond the control limits, no kind of trends or patterns. And I've also drawn spec limits on this chart. So here's my question. If the process remains stable, okay, I'm going to guarantee you that the process remains stable. My question is, are you comfortable that, say at least 99% of the product will meet specification. So I'm going to look at the chat window and see. So if you say yes, that means that you're comfortable as long as the process remains stable. It means that we're not going to violate these control limits. That the product would most likely meet spec. Yeah, Shauna, yeah, correct. The spec limits were set independently from the control limits. They should have been set independently. But given that I've set them here, here's where they are. These are the actual spec limits for this product, and these are the actual control limits. They were both set appropriately. So my question is, if the process remains stable, would you expect, say, at least 99% of the product to meet spec? I'm going to wait for a sample of about 5 or so answers. Yeah, Fred, you're ineligible. I've seen this too many times. So Tahir says yes. Dennis says not necessarily. Well, yeah, as far as the spec limits, should they be tightened? That's sort of, asking that question, that's sort of, I'll take that as you're saying yes, that the product's going to meet spec. So therefore we could tighten it. So a lot of yeses. And honestly, when I asked this question in my classes, they had a lot more time to think about it, a lot more stuff that's happened before. I'd say probably 75% say yes, the process will meet spec, if not higher. Sometimes it's 100%. The answer is no. Okay, absolutely not. Why? Well, the control chart is an X-bar chart. Each dot on this chart is a sample average. And when you average data, what happens to the variation? Variation gets averaged out, right? So in other words, if this represents a distribution of individuals, if I were to take 2 random points and average them, and do that a bunch of times, I would get this distribution. The variation would be this sigma over the square root of 2, square root of n. That's this standard deviation. And if I were to average over 5, I would get this curve. And average over 12, I'd get this curve. So you see, the distribution of averages gets very, very tight, and therefore the control limits, which involve square root of n in the denominator, get very, very tight when you average over a larger number. So it's a complete mistake to be comparing these averages to spec limits. In fact, here's actually, for some of these averages, I'm actually showing 6 individuals that make up this average. So 1, 2, 3, 4, 5, 6. The average of those is this dot. The average of these 6 x's is this dot. So you can see here, this process routinely produces non-conforming product, maybe what, 20% of the time? I don't know the total number. There's quite a few points beyond spec. Now, so the message here is, oh, well, we shouldn't use X-bar charting. The message is, we use X-bar charting for what it's intended for, to assess stability. It is not meant to make any decisions about capability, because we absolutely can't even think about how spec limits compare to averages. Can't do it. So I cringe when I go into a place and I see spec limits on control charts, even if they're on individuals charts, because then I'm worried they're going to end up on X-bar charts or other charts that they don't apply to. So, yet you'll find some pretty popular software that allow you to do this. Why? Because they want to sell software and their customers demand it. All right, the last thing in this section is just sort of a comparison of stability and capability. And hopefully I'm sort of starting to convince you that these are very different ideas. Stability, both this upper left and lower left are stable processes. I'm showing the distribution over time relative to spec limits. The fact that the distribution is consistent over time, I should have time in here. Time goes left to right. This one happens to also be capable, right? Meeting spec, probably a very high CPK. This one is clearly not capable. We're producing a decent amount of spec. On this side, we don't have a stable process, so questions about capability are kind of meaningless at this point. Yes, this is meeting spec, but if I were to calculate capability of this process down here, you tell me how confident you'd be that that would be predictive of my future capability, given that my process is all over the place. Okay? So stability, capability, different ideas. For us to even assess capability, we should be have evidence of a stable process using a control chart. Okay. How about sampling? This one can get a little kind of, I don't say tricky, but probably more, I don't want to try to keep this to an hour and allow questions to go over a little bit. So I'm not going to say too much about this, but the idea, I kind of alluded to this before. The control limits are supposed to reflect common cause variation. The way in which we collect data can either promote that or it could sabotage that. So let me show you a little picture here. So the other key thing I guess you have to understand is that these traditional charts like X bar R, X bar S, they assume that when you sample, you're getting what's called a rational sample. That means that every measurement that is inside my sample comes from a single distribution. That's clearly not the case, potentially, if you're pulling from different cavities or different filling heads or different locations on a part, if they're not running at the same mean. I mean, maybe everything's in spec, but if they're offset because the cavities weren't produced identically, say, then that's going to cause a huge issue in your control chart. Other violations could be maybe over time. The process will the common cause variation won't manifest over a short period of time, like in a continuous or batch process. Imagine you're looking at viscosity and you're melting, making glass, and you're pumping in some cullet from recycled glass, and you've got silica and all the things that go into glass, and you're going to take a bunch of viscosity measurements over a short period of time. You might see like the same number over and over. And so if you were to do that and construct control limits based on that, the control limits would be very, very tight because they're based on the within subgroup variation. Yet maybe over a period of 2 hours, some of the more common like how many impurities are in the cullet come in as we start mixing more and more into the batch, things change, the viscosity changes a little bit. And so now, if we were just to go with the original control limits based on short-term variation, we'd be seeing like process going out of control a lot. So you just have to think carefully about, is the sampling conducive to ensuring that the sources of common cause variation that we want to acknowledge, are they being represented within the samples? If not, then change your sampling or use a different method to establish the control limit. So you're looking at two options there. It'd be like, suppose it took you, another option would be, let's suppose it took you 2 hours to collect your sample. You waited 2 hours. And the process was running here, and then it was over here, and then it was here. But if you lump all this into one sample, you kind of think that this is your single process curve. And so you call all this common cause variation when the reality is common cause was much smaller. And so we've made it impossible to actually see these different processes as special causes. So, this is kind of an important topic. And we just need to think about how we're sampling. The traditional approach is, all right, take 5, wait, take 5 more. That's hopefully going to work most of the time, but sometimes you have to adjust your sampling to truly capture what you think to be the common cause variation. When you violate that, you get these kinds of control charts that you may think look wonderful, but they really reflect too much within subgroup variation because of non-rational samples. Number 7, I'm going to give you the idea. There's a lot more in here. There's an example. I like to go through it because it kind of results in a lot of light bulbs going off, but you can always review the slides after the fact, or of course, we'd love it if you were interested enough to take the course that Fred alluded to. But I want to at least give you the thought here. I mentioned it earlier, right? The purpose of control charts is to detect changes. Now, with individuals charts, you're kind of stuck with charts that don't detect small changes. That's just a fact of life. If you're stuck with individuals, then I strongly encourage you to use like a time-weighted chart, like a QSUM or EWMA chart. But the beauty of XBAR charts is that we can vary the sample size. And by selecting the subgroup size to be large enough, we can pretty much arbitrarily detect as small of a shift as we need to. So to just go blindly and say, well, let's do an XBAR chart. Oh, and the AIG manual says use 5. That's ridiculous. Okay? We need to be thinking about the size of shift that we need to detect. And maybe you have to know something to answer that question, like how good is my capability? How much is variation going to hurt? It begs the question, how much of a shift do we want to detect? And then we can take advantage of this, what I showed you before, which was as n increases, our expected variation among averages of that sample size gets less and less. As the sample size gets larger, we get our sample average gets closer and closer towards the true average. Okay? Control limits are going to get very tight. And so, what happens is, suppose we want to detect a shift from here to here, an average shift from here to here. We couldn't possibly do it with an individual's chart because the individuals are overlapping. But as you start increasing the sample size, and I'm skipping through this just to give you an idea of how the pictures change, the distributions get tighter. What does that mean? That when we reach a certain point, in this case n equals 12, the shifted curve, the averages from the process running at n equals 12 are basically all coming beyond the lower control limit of our original process that we were monitoring. So I will detect this with very high probability. All right, so the effective sample size on an XBAR chart is to help us distinguish or detect mean shifts as well as variation shifts. It's just a little more complicated. I have this little chart here that just sort of tells you, the probability of detecting, that's the power in this case, as a function of how big of a shift in terms of number of standard deviations in the sample size. And so I guess the sad thing here is that a typical sample size might be like 5. That's going to give a high probability of detecting about a 2 sigma shift, which I think is a fairly large shift. If we need to detect smaller shifts, like a 1 sigma shift, we either need more data or we need to use a different kind of a more sensitive chart. All right, I've got about 3 to 5 minutes left. So let me plow through this and then we'll stop for questions. I say here automate SPC. I mean, there's no reason you can't still plot these charts on paper or on the production line, how it used to be done. But that just makes it more difficult to identify signals, things like, a certain number of points trending or apply these different zone rules. We didn't go through the common, it's not just 1 point above or below a control limit. There's some other types of rules we typically look for. You sort of get to pick and choose. But with automated inline systems, you're controlling the process real time. You're able to react real time, get your operators involved real time, and it doesn't become an analysis exercise to try to go figure out what happened. Why did the process go out of control when I'm only diagnosing it a week later, right? That's not very proactive. So there's lots of options for automated SPC. Minitab does this, but that's more of a desktop package. But there are tools like, this is a picture of WinSPC from DataNet Quality Systems. They're one excellent package, and there are others. Another key cultural point, I think, is to think about how you're deploying operators in this process. In many places, the operators are not a big fan of SPC because they kind of view it as it's their braid, if you will, that's a stick. If the process goes out of control, then it's the operator's fault. And so what you sometimes see are operators over-controlling processes. They get near a control limit, and so they make an adjustment because, after all, they know more about the process than anybody. They certainly know how to shift it, and they're actually doing a lot more damage than than just by leaving it alone, right? Because they're introducing variation. I mean, I feel like when we've been given an opportunity to do some operator training, we don't do it at the same level that we do for the process engineer. Like they don't need to know necessarily how to determine sample size for a control chart, but they really need to know what the purpose of this tool is, how it's going to help them manage their process, control their process, how it's giving them an objective way to react, and how they're critical to the process because they're the ones that have to stop and try to diagnose what's going on. And in cases where it's done right, I mean, they are generally very excited. They feel like they're learning again. They a lot of times they get promoted into like an SPC coordinator position. So that's critical, I think, to the success is to ensure that the operators are involved in this process. And that ties in with the last point, which is like sort of managing the overall process, right? It's not just about seeing signals and saying, oh, that's nice, or oh, let's just make a quick adjustment. It went out of control. The purpose is to develop appropriate responses, like and have a process. Okay, if this process goes out of control, the operator does X, Y, Z. Maybe we'll increase the sampling. We need to get the right people involved to try to figure out why the process went out of control so that we can put some systematic longer-term improvements in place. I mean, the idea is that we systematically eliminate these special causes, and at the end of the day, that may not be enough because we may have too much common cause variation. That's a whole other ball game. But we at least have to follow through and not just stick the charts out there, but we have to have a business process in place that knows how to deal with reaction plans and sort of making this tool work better. As we improve the process, you know, if we reduce variation, guess what? We can be more efficient. We can reduce the sample size we need. So things get cheaper as we get better. You have to, you know, update the charts. Maybe a chart we needed before is now a different chart today because of the way it's improved. So it's sort of an ongoing thing. All right. So I know that was a lot of material. I always struggle with what do I cut out. So anyway, thanks for your patience. I know there were some comments coming in, but I would like to open it up to formal questions. I will go back and try to pick up some of the previous comments that were made. And thank you, Fred, for commenting and for managing some of the comments that were coming.
Dennis or Stephen, and Dennis has been chiming in quite a bit too. He's another author on, at least I think it's the Dennis I know, is been writing about these very topics also in a series of articles on Sendo. And I know some of the questions that came up, Stephen, were you know, the connection between, or the independence of setting specifications from setting control limits. And I think they're different activities, yet at the heart of both of those things is that standard deviation. And so to set appropriate tolerances, that's a balance between what's possible and what's needed for the functionality. I think understanding that standard deviation is pretty important. And I don't know.
Yeah, I agree. I mean, from the perspective of where we maybe need to set a specification, but we don't really know from a theoretical perspective what that needs to be. We could do some experimentation, but we might want to say, you know, let's base specs based on what our current capability is. Then you're right. We need to know how much variation can we maintain. And that could be involved in setting specifications. I guess on my ivory hat, I like to think about specs are independent of the actual process variation. They are driven purely by what are the product requirements and what specifications are needed from materials, from dimensions to ensure that those requirements are met. So theoretically, if everything meets spec, we should never have a quality or reliability issue. I realize that's sort of wishful thinking, but yeah, I agree with you. In many cases, especially in manufacturing specifications, we are relying on understanding of variation to set specs, but just keep in mind that specs set there are based on the standard deviation of individuals, and control limits are often set on standard deviations of averages, or standard deviations of proportions, or
That's right.
standard deviations of a range,
Yeah.
right? It's a different.
One question I have for you is, and you've been seeing a lot more implementations because it's a big part of your business, um, is I have not seen a very well done automated SPC process. It seems to be, oh, let's buy the software and then our operators don't have to deal with it, right? I've not seen it where they actually use it. The best implementations I've seen are paper, and the operator is filling it out real time and understands it. And so there's a key connection there. But I see the automated ones being a proxy
Yeah.
too often. Maybe I have a limited sample size.
Yeah, I mean, there's like a lot of truth to what you're saying. It's unless the operator is, processes, the operator shall spend X amount of time, reviewing what the computer is spitting out and taking actions. Um, but I've seen cases where, they simply routinely they just have to check a box saying they saw the signal and everything's good, and
Yeah.
they always check the box. So, yeah, Dennis, to your point here about much of SPC assuming data is normally distributed, and that's interesting. Certainly, I think it depends, right? If you're doing X bar charting, because of the central limit theorem kicking in, we can generally be pretty comfortable that the control limits are going to be reasonably accurate at plus or minus 3 standard deviations of the averages, even if the raw data is non-normal. Now, a lot of other consultants like Wheeler, they'll get very angry if you say that control limits have anything to do with the normal distribution. It's my view, though, if you're charting individual data, you're dealing with a very skewed distribution, which sometimes we have, like the microbial content, where you get some occasional large values, but my belief that we ought to reflect the non-normality in the control limits, which is not a big deal. You could fit a log normal or Weibull distribution to your data and develop more appropriate limits of expected variation. To me, that will eliminate, reduce the occurrences of false alarms, where you're reacting based on 3 signal limits, when in fact the process is doing what it's expected to do. Yeah, I agree with you too. Now, capability is another issue where normality becomes critical, right? Because here you are dealing with individual data, and there are, as we cover in our course, there are certainly very good methods for modeling non-normal data and basing capability calculations.
Yeah. And I know that you go into this in pretty good detail in the course, is dealing with non-normal data. It's the part where I stopped and took more notes about the content than actually the recording and how I was going to produce the material. So I knew it was good stuff because I certainly learned a lot myself. And so one more blatant plug for the course there, Stephen. All right. Well, I know it's a little bit past the hour. We've got folks who are dropping off, which is we usually build these for an hour, and then people schedule time for that, and then they head out. For those that participated, and Dennis in particular, thanks for chiming in, putting us all together, and helping with the comments and reinforcing some of those critical points. And Stephen, thanks so much for sharing this. I know it's a lot of material. It's just a thumbnail of what we go through in the course, or what you go through in the course. And I think you typically do this kind of presentation over an hour and a half or 2 hours, but our format here is we're much more successful carving out an hour for people's time. So, but either way, Stephen, I really appreciate you going through this stuff. Things like sample size, how and where you take your samples are the key takeaways, at least for me. And with 10 main points you made, I'm sure others will have different sets that they're looking for. Stephen's got his final slide up here that has where you can find more about it, the company that he's in, integralconcepts.com, and the work they do. I know he's a wizard with Minitab. I've seen him do amazing things with that. So him and his wife are really good at applying statistics in a meaningful way across a lot of different applications. And so get a hold of them if you need their help. But in in the short term, I'll just say thanks again, Stephen, and we'll see if we get you back on for another one of these at some point, because it's and what I'll do then, Stephen, is I'll give you like a more narrow scope instead of 10 things. We might pick one.
You better give me a
Very good.
slide limit too, like not to exceed. No, thank you. Yeah, I appreciate the opportunity to spend some time with your Ascendo community, and yeah, thanks to everybody for the interest,
All right.
questions, and everything.
All right, great. Well, I'm going to wrap it up here. I'll hit the end record and.